Hello everyone, and welcome back to another GIS lecture video. And in today's GIS lecture video, we're going to continue our discussion on GPS, specifically talking about how we're actually able to convert this conceptual model with the space segment, the control segment, and the user segment into something that sort of explains a little bit better about how we're actually able to calculate a position with any degree of accuracy at all. And so what we're going to be talking about primarily in this video is actually going to be concerning this piece right here. This yellow line that connects the space segment, which is sending out a signal, to the user segment, which is you with a GPS receiver, receiving the signal. We're going to talk about what's actually coming, at least in part, in this signal that's going to allow us to actually do something called trilateration. And we'll talk about trilateration in more detail in just a second. But for this video, we're largely focusing just on the satellite and the receiver. So let's go ahead and give ourselves a little bit more space here. So let's go ahead and imagine this is you in space, right? You have no idea where you are at all. Luckily for you, though, you have a GPS receiver that is attuned to talk to several satellites. And we will say, for the sake of argument, that we have 3 satellites. We have satellite A, we have satellite B, and we have satellite C. Right, great. Well, now we know we have some satellites, but that still doesn't help us, right? We have no idea where in the blackness of space we are. So how are we going to do, what are we going to do about that? Well, the first thing we need to do is figure out how far away we are from the satellite. That's the first step. Okay, so the first thing we want to do is figure out how far away we are from each satellite. All right. So without going into too much detail, basically, we can figure out how far we are away from each satellite by using something called pseudo-range. And pseudo-range is just a fancy term for the distance. Right, the distance between you and a satellite. Right, the distance between you and a satellite. So what we can do is we can capitalize on the fact that the information, right, that data that we talked about in the previous video is actually a form of electromagnetic radiation, right? So the satellites and the receivers communicate between each other using electromagnetic radiation, right? So communication is done with electromagnetic radiation, right? It's a special wavelength of light. I'm going to underline electromagnetic radiation here because this is going to be very important, right? It uses electromagnetic radiation. And we're going to spend a whole lot of time talking about electromagnetic radiation and the electromagnetic spectrum in later videos when we talk about remote sensing. But for right now, the key thing to understand here is that the communication between you and the satellite is done with electromagnetic radiation. And that gives us a very important piece of information because electromagnetic radiation, among other things, moves at the speed of light. Right? We know through extensive testing done over many, many decades, right, we know a lot about electromagnetic radiation. And one of the things we know is that it moves at a constant speed. And that speed is the speed of light, which you will often see denoted with a lowercase c, which now I'm realizing that this satellite C might get confusing. But this C here, this is a constant for the speed of light. And basically what that allows us to do is we can use this fact, right, that the communication is done using electromagnetic radiation, which moves at a constant speed, right? We can use that to figure out this pseudo range, right, the distance between you and the satellite, which is what we're trying to figure out. So what happens is you are constantly communicating with all of these satellites because you have a GPS receiver, right? You have the user segment, the satellites are the space segment, and they're constantly communicating with electromagnetic radiation that moves at the speed of light. So we have one piece, we have speed. We also, in order to do anything, would need to know where these satellites are. Well, luckily for us, we know where all these satellites are, right? Satellites have their position calculated precisely using orbits, right? We know how to calculate the orbit of a satellite. It's way outside of the scope of this class, but it's something that we certainly know how to do, right? So we know, right? We know the position of the satellite. Because we can calculate orbits. Right? We've known for a long time how to calculate the orbit of something going around the Earth. Right? So we know the position of all of these satellites, right? A, B, and C. We know their position relative to Earth because we're able to calculate that using physics and mathematics. We know the speed at which the signal that we're communicating with is traveling because it's electromagnetic radiation. Right? There's only one other piece we need, and that is to know when the signal was sent. Right? Well, we also have that information because satellites have on board very sophisticated clocks, right? GNSS, right? Global Navigation Satellite Systems, which is the broader version of GPS, right? Satellites have very accurate clocks, right? Very accurate clocks. So we know that we have the position of the satellite because we can calculate its orbit. We know that we have the time on the satellite because satellites are built with very accurate clocks. And we know that any communication done between the receiver and the satellite is moving at the speed of light. So we have these three key pieces of information. We have the position of the satellite, the time that any communications are done at, and we have the speed at which the signal is moving. So let's go ahead and let's clean up this figure a little bit. Okay, so I've cleaned it up a little bit, so we still have our three satellites. So what do we know from what we just talked about? Well, we know that satellite A is broadcasting a constant signal with its position and the time, right? We know that satellite B is broadcasting its signal with its position and time, right? Because these are the two things that we say we know because of various setups within the satellite. And we know that satellite C is also sending out a signal with its position and its time. So what does that allow us to do? Well, if you are somewhere in space and you get a reading from A, satellite A, saying, hey, I'm right here, and I sent this signal at this time, what we can do is we can actually calculate our distance away from that satellite. Right? So we can calculate our distance away from A. We can calculate our distance away from A. Let's use white. All right, we can calculate our distance from A. All right, we can calculate our distance from A. This distance. All right, we can calculate this distance. All right, this distance, because we know the position of the satellite, we know the time that it was sent, and we know the speed the signal was moving, right? Because again, it's moving at the speed of light. And so there's a basic physics equation, right? That says distance equals velocity times time, right? This is a basic physics equation. Distance equals velocity times time. Well, what do we know? We know the velocity, right? This velocity piece here is the speed of light. Or c, right? And we know this time here, because this time is just, right, the time that the signal was sent compared to the time the signal was received, right? So this is the time received minus the time sent, right? And that allows us to calculate our distance, right? Because we know the velocity because we know it's the speed of light. We know the time because it's sending from an accurate clock and we're receiving it with a clock. So we know the time that the signal traveled. So we multiply the time the signal traveled by the speed, and that gets us the distance. We set the position of the satellite, which was also sent, at the center, and we make a circle of that distance, right? And now we know with some level of certainty that we are somewhere on this circle, right? And this distance, right, again, this is called pseudo-range. This is your pseudo-range. Is this distance from the satellite, some distance. We don't know where, right? We know, we are confident that we are somewhere on this circle. That's all we're confident about. But we have more than just A, right? Because again, we're constantly communicating with all three of these satellites. So we are also, at the same time we're receiving a position and time from A, we're also receiving a position and time from C. Right? And so we do the exact same thing, right? We can draw a circle, although my drawing skills leave a little bit to be desired here. You can imagine that this should be a perfect circle, right? And we know that we are also getting, right? We know that we can also get the distance from C, right? We can get this distance. Again, right? Distance equals velocity times time. This is giving us a timestamp for when it sent the signal. We know the time we received it. We know the velocity. We multiply those together, set the position at the center of a circle, and we can create the exact same thing we did with A. So now we have two pieces of information, right? Meaning we know where this distance away we lie on this yellow circle from C. We know that we're this distance away lying on this circle from A. And visually what that means, right, is that we would have to be where these two things are both true. Visually, that means we have to be where these two circles intercept. So we would have to be either here or here, right? Because that's the only place where the distance we're supposed to be from C and the distance we're supposed to be from A, right? But we can do one better, right? Because if we stopped right here, right, we would have no way of knowing whether we're here or here. And depending on how far away this distance is, that could be miles, right? Hundreds, thousands of miles, potentially, right? The difference between here and here. And we would have no way of knowing. But we can do one better. Right, we can do one better because we have the same distance equation for B, right? I'm going to draw it because it's going to definitely cause me a little bit of problems here. So I'm going to do my best here to try and draw a circle from B. It's going to go off the screen a little bit, but that's okay. Try not to interrupt the writing we have too badly. Right? Again, imagine this is a perfect circle here. Right, but we also know we have that exact same information that we had before, we have from B as well. Right? We know that we are some distance from B. Right? We know we are some distance from B. Because again, right, the same thing. Right? We know the position of B and the time, multiply it together to get the distance. So what does that mean? Well, with this third piece of information, right, we now know that this piece over here can't be true. Right? I'm going to try my best to cross that off. Right? This cannot be true. Right? Because the only place where we meet the criteria for being a set distance from A, a set distance from C, and a set distance from B is where all three lines overlap. And that only place that could be, the only place that could be is here, right here. So this right here, this is our true location with some error. And we'll talk about that error part later. But so to wrap up, right, this setup right here, these three satellites communicating their distance based on position and time, this is called trilateration. Let me scoop up just a little bit. Right, this whole process that we just described, this is your trilateration. Trilateration, right? This trilateration is the fundamental concept for how GPS works. And again, it's based on a position coming from the satellite based on its known orbit, the time the satellite knows that it sent its position, and then we use that along with the time that we received the signal and the speed of light, which is a constant, to calculate this distance, right? The speed of light times time, which is again the time that we received the signal minus the time the satellite says that it sent it. That gives us the distance. We can compare our distance to 3 or more satellites to be able to get our position. Now, before we end the video, I want to sort of emphasize that this is a very simple, stylized example in 2 dimensions. When we move on to 3 dimensions, right, because we live in a 3-dimensional world, these would actually become spheres instead of circles. And you would end up wanting to have at least 4 or more satellites to help pinpoint this location with any level of accuracy. And we'll talk about error in a minute, which helps explain that. But also because when you deal with 3 dimensions, you really want a minimum of 4 satellites. So hopefully this stylized example makes sense of what trilateration is and how it works. And as always, if you have any questions, please reach out. Thank you.